I wish I could tell you that evaluating limits was as simple as just plugging numbers into the functions, but lying to students is generally frowned upon. So let's look at an example of where just plugging in the number that x is approaching doesn't work. Example, evaluate the limit as x approaches 2 of x minus 2 over x squared minus 4. If I try to plug in x equals 2, I run into a problem. 2 minus 2 over 2 squared minus 4 is equal to 0 over 4 minus 4, which is equal to 0 over 0. You might remember that 0 divided by 0 is an example of something called an indeterminate form because it could be anything. What we can say for certain is that x equals 2 is not in the domain of the function x minus 2 over x squared minus 4, which is why our shortcut of just plugging in 2 didn't work. So what do we do now? Once we've tried plugging the number in, if that results in an indeterminate form, our next strategy is to try using algebra to simplify the limit and then try plugging in the value again. What algebra can we do to simplify the limit as x approaches 2 of x minus 2 over x squared minus 4? We have a rational function, in other words, a ratio of polynomials, so we can try factoring to see if anything cancels. The numerator x minus 2 is already as simple as it can be, but the denominator x squared minus 4 is a difference of squares, so we can factor that as x minus 2 times x plus 2. Since we have a common factor of x minus 2, we can cancel it. So the limit as x approaches 2 of x minus 2 over x squared minus 4 is equal to the limit as x approaches 2 of 1 over x plus 2. I want to pause here and make a subtle but important point. It is true that the limits are equal, but the functions x minus 2 over x squared minus 4 and 1 over x plus 2 are not equal, because they have different domains. One is defined at x equals 2 and the other is not. If we think back to graphing rational functions from pre-calculus, the function y equals x minus 2 over x squared minus 4 has a hole at x equals 2, but the function y equals 1 over x plus 2 does not. Other than that one tiny difference at x equals 2, these functions look identical. And since limits are only about what happens as we approach the value, not what happens at the value, the two functions have the same limit as x approaches 2, even though they don't have the same value at x equals 2. What does this mean for you? Well, in addition to being an important reminder about what limits represent, this also means that we have to be careful with our notation. We must continue to use the limit notation throughout our work until we get to the very last step where we plug in an actual number for x. So to do this problem correctly with precise notation, we write that the limit as x approaches 2 of x minus 2 over x squared minus 4 equals the limit as x approaches 2 of 1 over x plus 2 equals 1 over 2 plus 2 equals 1/4. In summary, when evaluating limits, first try plugging in the value for x. If you get a number, awesome, you're done. If you get 0 over 0 or another indeterminate form, use algebra to simplify, then try plugging in the value of x again.